Hi, today we'll see FPGA which comes under Module 3 Implementation Fabrics. Previous slides and all you might have heard about this term. Now we'll study in depth about this FPGA. FPGA is nothing but Field Programmable Gate Array. The full form is Field Programmable Gate Array. It is an IC designed to be configured by a customer or a designer after manufacturing. Hence the term field programmable, because it will be done by the customer or the designer after the manufacturing. Hence the name we'll call it as field programmable. The FPGA configuration is generally specified using a hardware description language similar to that used for an application specific integrated circuits. The circuit diagram were previously used to specify the configuration, but this is increasingly rare due to the advent of electronic design automation tools. So I have just shown you that Spartan FPGA from Xilinx. So this is how an FPGA IC looks like. FPGA contain an array of programmable logic blocks and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together like many logic gates that can be interwired in different configurations. Logic blocks can be configured to perform complex combinational functions or merely simple logic gates like AND and XOR. In most FPGAs, logic blocks also include memory elements, which may be simple flip-flops or more complete block of memory. Many FPGAs can be reprogrammed to implement different logic functions, allowing flexible reconfigurable computing as performed in computer software. So this is the internal organization of an FPGA. You can see over here it consists of so many things like LB. LB is nothing but logic block. Next is IO. It is nothing but input output blocks, and then you can see it is nothing but embedded RAM, and you can see it is all those things are etched in a gray color background, which is nothing but programmable interconnections. I'll just tell you all those things once again. We have an array of logic blocks that can be programmed to implement simple combinational of sequential logic functions. So we are having an array of logic blocks in the previous diagram. You can see over here. You can see here logic blocks are there. What is the function of those things is it can be used for programming. And next is input output blocks that can be programmed to be registered or non-registered, as well as implementing various specifications for voltage levels, loading and timing. Next you can see the embedded RAM blocks over there. And last you can see a programmable interconnection networks. The basic elements within logic blocks are small 1-bit wide asynchronous RAMs called lookup tables, LUTs. The LUT address inputs are connected to the inputs of the logic block. The content of an LUT determines the value of a Boolean function of the inputs, but by programming the LUT content differently, we can implement any Boolean function of the inputs over there. The logic block also contains one or more flip-flops and various multiplexers and other logic for selecting data sources and for connecting data to adjacent logic blocks. So you can see a logic block example over here. I have taken a Spartan 2 FPGA logic block over here. Here you can see the LUT. You can see a carry and control logic. You can see flip-flop over here. I'll just brief you out all those things. The logic block contains two slices together with a small amount of additional logic. Each slice consists of two 4-input LUTs, each of which can be programmed to implement any function of the 4 inputs. You can see over here, you can see 4 inputs are there for the LUT. The carry and control logic consists of circuitry to combine the LUT outputs and an XOR gate and an AND gate for implementing adders and multipliers, as well as multiplexers that can be used to implement a fast carry chain. A number of connections within the control and carry logic are governed by the programming of the FPGA. The logic block contains SRAM cells for these programming bits. In contrast to LUT based logic blocks, which can implement relatively complex functions, some FPGA have more fine-grained logic blocks also. Now I'll just show you the IO blocks which is there in the FPGA. So you can see here flip-flop, you can see here marks, you can see here tri-stage buffer, as well as you can see some resistors. I'll just brief out that the select inputs of the multiplexers are programmed to control whether the output is registered or combinational. The top flip-flop and multiplexer control the high impedance state of the tri-state drivers that drive the pin as an output, and the middle flip-flop and the multiplexer drive the output value. You can see in the previous diagram, flip-flop is there, middle flip-flop which we are talking about, the middle flip-flop as well as the multiplexer we are talking about. So you can see what they are specifying, the flip-flop, middle flip-flop and multiplexer drive the output value. You can see here it is driving the output value. The output driver is programmable, allowing selection of logic levels and control of slew rate, that is rate of voltage change at the output. The input buffer is likewise programmable, allowing selection of threshold voltage and other characteristics. The pull-up and pull-down resistors are programmable, allowing them to connected and their resistance to be selected. Now we can see other two topics, which is nothing but platform FPGAs as well as structured ASICs. So first I'll tell you about the platform FPGAs. In order to improve the usability, manufacturers have added specialized circuitry to the larger recent FPGAs, including processor cores, computer network transmitter and receiver, as well as arithmetic circuits. Such FPGAs are often called as platform FPGAs. It means that the chip serves as a complete platform upon which a complex application to be implemented or can be implemented. Embedded software can run on the processor cores with instructions and data stored in the block RAMs. The network connections can be used to communicate with other computers and devices. The programmable logic and specialized arithmetic circuits can be used for high performance data transformations required by the application. A minimal amount of circuitry is required externally to the FPGA, thus reducing the overall cost of the system. So platform FPGAs are now recently used more because it will reduce the cost as well as the performance will be more. Now we'll move on to the next topic, structured ASIC. It is recently used by all the manufacturers that they develop a new kind of IC called structured ASICs, that is midway between PLDs and standard cell ASICs. A structured ASIC is an array of basic logic elements or components like FPGA. It is not programmable and omits the programmable interconnect. The logic elements are generally very simple, comprising a collection of transistors that can be formed into logic gates and flip-flops, whereas an FPGA is customized by loading a configuration program. A structured ASIC is customized by designing the top one or more layers of metal interconnection for the chip. Since the underlying logic elements and lower interconnection layers are fixed, the design effort and NRE cost for customization are much lower than those for standard cell ASIC. Further, since the structured ASIC is not programmable, just customized by a design and manufacturing process, the performance is potentially very close to that of a standard cell ASIC. Many observers expect that structured ASIC will become popular for complex medium to high volume application over the next few years. So recent technology, they are preferring almost all the manufacturers are preferring structured ASIC. So with this I am stopping, and next topic will be IC package and PCB. Until then, thank you.